This is Bob Capetta, and this lesson is on permutations. So a student has the following Hemingway books: A Farewell to Arms, which I'm going to label as A. The Sun Also Rises, I'm going to label as R. The Old Man and the Sea, I'm going to label as S. And For Whom the Bell Tolls, I'm going to label as T. She needs to decide how to organize these books on a shelf. How many different arrangements are possible? So which book is first, which book is second? Which book is third? Which book is fourth? That's the question we're asking ourselves. So we can list all the possible arrangements here. What are they? Well, again, A, R, S, and T, and I'm going to try to write these in alphabetical order. That's one way to sort of keep it straight. So the first one I have is A, R, S, T. So A Farewell to Arms first, then The Sun Also Rises, then The Old Man and the Sea, and then For Whom the Bell Tolls. Then A, R, T, S. Then ASRT, ASTR, ATRS, and ATSR. So those are all the ones that have A Farewell to Arms in first position. Next, I'm going to put Sun Also Rises in first position. So if that's the case, RAST, RATS, RSAT, RSTA, RTAS, RTSA. So those are 6 ways to organize it with The Sun Also Rises in the first position. Then we have The Old Man and the Sea in the first position. Similarly, SART, again alphabetical order, SATR, SRAT, SRTA, STAR, STRA. And finally, For Whom the Bell Tolls in the first position, and you can see all of those. Now that's challenging to think through all of those organizations, all of those arrangements of those 4 books. But what I've shown is that we have a total of 24 possible ways to arrange 4 books on a shelf. So ARTS is what we started with, but there's 24 different ways that we can do that. So this is actually a permutation. That's a term we're going to use in this lesson. It's a permutation of 4 letters choosing 4 positions. Now, we can actually determine the number of these arrangements by using the fundamental counting principle. So we have 4 books to choose from. There are 4 choices for the first slot, first in line. It could be A, it could be R, it could be S, it could be T. Once I choose that first position, now I have 3 choices for the second position, second in line. Once I choose those 2, there's only 2 left, so 2 choices for the next one. And then the last one is already determined. There's only 1 choice left. So we know we can multiply those together. 4 times 3 times 2 times 1 will give us the total number of arrangements of those 4 books on the shelf, 24. But again, that's going to correspond to a permutation. Permutations look at things in order. How many different orderings do we have? 4 items choosing 4 slots. There will be a permutation of 4 on 4. But before we get there, let's talk about factorial notation, the exclamation point you may have noticed. So 4 factorial is what we had previously, 4 times 3 times 2 times 1. So the number of arrangements here was 4 factorial. 4 factorial, 4 exclamation point is 4 times 3 times 2 times 1. So then 5 exclamation point is 5 times 4 times 3 times 2 times 1. 6 exclamation point, 6 times 5 times 4 times 3 times 2 times 1, etc. So factorials, you start with the largest number, decrease by 1 until you get to 1 and multiply everything. That's our notation. So let's do a little bit of arithmetic with some factorials. So if I have 8 factorial divided by 6 factorial, what will that be? Well, 8 factorial, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. A lot of things cancel. So what cancels? 6, 5, 4, 3, 2, 1 here, 6, 5, 4, 3, 2, 1 there. So I'm going to put those in parentheses just so that you can see that they're going to cancel, they're going to divide out. So what's left upstairs is 8 times 7, what's left downstairs is 1. So we just get 8 times 7 times 1, or 56. So 8 factorial divided by 6 factorial is 56. And let's do one more arithmetic problem. We will look at 9 factorial divided by 12 factorial. So a larger number is on the bottom this time. 9 factorial means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 12 factorial, 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And of course, a lot of things are going to cancel. So 987654321 on the top, 987654321 on the bottom, which will just leave a 1 on the top. On the bottom, what are we going to have? So you can see what's in parentheses is going to divide out. This divided by this is the same as 1 over 1. So 1 upstairs, 12 times 11 times 10 downstairs. So 9 factorial over 12 factorial, 1 over 12 times 11 times 10, 1 over 1,320. So factorial notation will be useful for us when we are computing permutations, numbers of permutations. So here we go. There are 30 members of a union, and they need to elect a president, a vice president, a secretary, and a treasurer. So we're ordering 4 people from a total of 30. So being selected president is not the same as being selected secretary. So let's assume they select the president first, then they select the vice president, then the secretary, then the treasurer. So how many different ways can we do this? Well, we can answer that question using the fundamental counting principle. So 30 possible choices for president. Every person in the union is eligible. 30 possible choices for president. But once that person is chosen, now we only have 29 possible choices for vice president. Once those 2 people are chosen, there's only 28 choices for secretary and 27 choices for treasurer. So how many different ways can we arrange 4 selected people from a group of 30? Using our fundamental counting principle, that will be 30 times 29 times 28 times 27, which is how much? Which is 657,720. So you'll notice as we're working with permutations, some of these numbers get very large. Now here's our formula. NPR, the number of possible permutations if our items are taken from a total of n. N in our entire group, we are selecting for an order matters. So I like to consider them arrangements. Arrangements of letters, arrangements of people, arrangements of items. Like we had arrangements on the shelf, we had arrangements in offices. So here's our formula. We have n people, and we're going to select 4 from that group for specific offices, so the order is going to matter. That is a permutation. So this is our previous example. 30 members, and we're selecting 4 from that group, so it'll be 30 pick 4. So the permutation of 30 with 4 will be what? N is 30, so 30 factorial, and minus r, 30 minus 4, 26 factorial downstairs. So indeed, how are we going to go ahead and do this computation? We'll think about it. 30 factorial, 30 times 29 times 28 times 27 times 26 times 25, 24, 23, 321. 26 factorial, 26 times 25 times 24 times 23, 321. So a lot of stuff cancels. So you'll notice what I have here. 26, 25, 321 on top, 26, 25, 321 on the bottom will go away. What will that lead me with? 30, 29, 28, 27, which you'll recognize from my fundamental counting approach. 30 choices for president, then 29 for vice president, then 28 for secretary, and 27 for treasurer. So you see this model agrees with the way that we did this previously. 30 times 29 times 28 times 27 again. 657,720 ways we can arrange 4 people from a group of 30. Okay, here's our next example. How many 5-letter words with no repeated letters are possible from an alphabet with 26 letters? So Bob, my name is not going to work because we have repeated B's. Plus it's only 2 letters. If your name was Rosie, R-O-S-I-E, that would work because that's 5 letters and no letters are repeated. So how many different words in quotes, so these are not words in English, these are just possible arrangements of 5 letters taken from 26. Whoops. So what do we have next? So here we go, A, B, C, D, E, A, B, C, D, F, A, B, C, D, G, Z, Y, X, W, V, etc. So again, if we think about the fundamental counting principle, first slot I have 26 choices. Second slot, 25 choices. Third slot, 24 choices, etc. Right? 26 for the first letter. 25 for the second letter, again, because no letter can be repeated. That's our issue. 24 for the third letter, 23 for the fourth, and 22 for the fifth. So those are all of our possibilities, number of choices. So if we use the fundamental counting principle, we'll get 26 times 25 times 24 times 23 times 22, which gives us 7,893,600 possible five-letter quote-unquote words with no repeated letters selected from an alphabet of 26. Now let's do this with a permutation. We're looking at arrangements. So certainly the order matters for words. So we're starting with 26 in our large set. We want to select arrangements of 5. So we're looking at 26 pick 5 permutation of 26 over 5. So 26 pick 5 is 26 factorial over 26 minus 5 factorial. 26 factorial over 21 factorial. Now what is 26 factorial? 26 times 25 times 24, 23, 22, 21, 20, 19, 18, 17, 3, 2, 1. 21 factorial, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of it cancels. All we are left with when it divides out is the 26 times 25 times 24 times 23 times 22. Okay, that's what we had before, right? 26 choices for the first letter, 25 for the second, 24 for the third, 23 for the fourth, and 22 for the fifth. So that's the same number that we had before, 7,893,600. So now we're going to look at shuffling. So we had no repeated letters previously. Now we're going to look at repeated letters. So again, back to my name of Bob. How many ways can we shuffle those 3 letters? I want to do this in alphabetical order just to keep it straight. BBO would be the first one in alphabetical order. Then BOB. And finally OBB. Any other ways to shuffle those? I don't think so. So that gives us 3 ways to shuffle BOB. How about auto? How about auto? So we're going to start in alphabetical order, so O comes first. So OOTT would be my first one in alphabetical order. OTOT. Then there's auto. So I think those are all the ones that start with O. If I start with T, TOOT, TOTO, TTOO. So we have 6 ways we can shuffle auto. And here is our formula. Permutations of duplicate items. The number of permutations of n items where p are identical, q are identical, r identical, and so on is given by that formula. A little hard to understand. I think it's easier to understand if we look at these examples. Bob and his 3, Otto and his 4. The letters downstairs, P and Q. B is there twice, so P will be 2. Q is there once, Q is 1. For Otto, O is there twice, P is 2. T is there twice, Q is 2. So again, Bob has 3 letters, so N is 3. 2 B's, P is 2. 1 O, Q is 1. So 3 factorial over 2 factorial, 1 factorial. That's a number of distinguishable permutations. That's what I like to call it. 3 factorial over 2 factorial, 1 factorial. 3 factorial is 3, 2, 1. 2 factorial is 2, 1. 1 factorial is just 1. 6 divided by 2 is 3. And that's what we had, remember? We only had 3 ways to write Bob. BBO, BOB, and OBB. So that was our number of distinguishable permutations for Bob. Now we also need our number of distinguishable permutations for Otto. So Otto has 4 letters and is 4. The number on top will be 4 factorial. 2 O's, 2 factorial downstairs. 2 T's, 2 factorial downstairs. So n factorial over p factorial, q factorial if there's just 2 letters. So 4 factorial over 2 factorial, 2 factorial. 4, 3, 2, 1, 24 on top, 2, 1, 2, 1, 4 on the bottom. And I just get 6, which is again what we saw. We had 6 ways we could shuffle up Otto, 3 ways we could shuffle up Bob. Those are the number of distinguishable permutations, permutations of duplicate items. And the last thing I want to do in this lesson is find out how many ways can we shuffle the letters of Mississippi. So I need N. How many letters are in this list? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 letters in Mississippi, so N is 11. Now what are the different letters? M. M is there how many times? Just once. So P is 1. I is there how many times? 1, 2, 3, 4. I is there 4 times, so Q is 4. How about S's? 1, 2, 3, 4. 4 S's, so R is there 4 times. We need one more letter, though. We need P's. P's are there twice. 2 P's, so S is 2. How many ways could I shuffle up the letters of Mississippi? That is our question. So upstairs 11 factorial, downstairs 1 factorial, 4 factorial, 4 factorial, 2 factorial. Okay, again 1 factorial, 4 factorial, 4 factorial, 2 factorial. What is 11 factorial? 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 1 factorial is just 1. 4 factorial is 4, 3, 2, 1. 4 factorial is 4, 3, 2, 1. 2 factorial is 2, 1. One thing to note, 0 factorial equals 1. That might become important sometime, so just keep that in mind. 0 factorial is 1. All right, so here's our number of distinguishable permutations. 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 1, 4, 3, 2, 1, 4, 3, 2, 1, 2, 1. We need to simplify this some way. Well, you can see the 4, 3, 2, 1s are going to divide out quickly. So I'm going to put those in parentheses and divide those out. So the 4, 3, 2, 1s will go away. So upstairs I just have 11, 10, 9, 8, 7, 6, 5. Downstairs this 4, 3, 2, 1 and that 2, 1. 4, 3, 2, 12 times 2 is 24, times 2 is 48. So downstairs I have 48. But what is 48? 48 is 6 times 8, so I guess I can divide out that 6 and the 8. That'll leave me with 11, 10, 9, 7, and 5. And what does that give me? 34,650. Now certainly a calculator or a computer will help you with some of these more challenging computations. So I'm going to quickly show you how you can evaluate this on Excel. So if I want to do 11 factorial, the command on Excel is equals fact, F-A-C-T, parentheses 11, hit enter, and it will give you 399,16800, a very large number. So what I'm going to do is I'm going to do 11 factorial, 1 factorial, 4 factorial, 4 factorial, 2 factorial. So this is the syntax. 11 factorial equals fact 11, 1 factorial equals fact 1, which is just 1. 4 factorial is equals fact 2, 2 factorial equals fact 2. So I built a little spreadsheet with those numbers, and there they are. There's 11 factorial, 1 factorial, 4 factorial, 4 factorial, 2 factorial. Take this divided by this times this times this times this, and there is my answer of 34,650. And that will conclude this lesson.